Welcome to second week Go seminar. Today's speaker is Nikolaos Melissinos, and he will tell us something about parameterized distance to local irregularity.
Thank you so much for the introduction. So this is a joint work with Fioravantes and Theophilos Triomatis. And in this talk, we're going to talk about distance to local irregularity. But what is local irregularity? Let me start with some definitions. So first of all, what is an irregular graph? Irregular graph is a graph where any pair of two vertices have different degrees. However, someone can realize that this is a really strict notion, and the only graph that you can imagine is just one vertex. So for that reason, well, that was introduced already in 1988, and because this is a really strict notion, there is this other notion introduced 2015, which is local irregular graph, and there you want two adjacent vertices to have different degrees. So this has been already used in some works, have some connections with proper edge labelings, and there are some nice structural properties when you can decompose your graphs into some small number of local irregular graphs, and that's why we're finding it interesting. So what are the problems that we're going to discuss in this talk? The first one is vertex distance to local irregularity, which has already been introduced a few years ago. And there you want to delete the minimum number of vertices such that the remaining graph is locally irregular. And the second problem is edge distance to local irregularity, where you want to delete only edges from your graph and the resulting graph to be locally irregular. Let's see some examples. So giving this example, I'm asking how many vertices do we need to delete in order to have a locally irregular graph? An obvious answer is 1, right? If I'm deleting that one, then all the middle vertices have degree 2, all the other vertices have degree 1. We are happy. But what happens if I'm asking how many edges do we need to delete? Then we need to take some time to realize that all those colored pairs have the same degree. We cannot delete just one edge in order to fix all of them in the same time. So we actually need to delete n edges in order to have a locally irregular graph. And you can see that I also have an isolated vertex. I have no problem with that. So let's see another example. The same question here, well, the reverse question first. How many edges do we need to delete here? So let's take a look. We see that we have n square copies of this gadget there in one side, n square copies of the same gadget in the other side. So the top two vertices have a problem. They have the same degree. So we can delete just one vertex and everybody is happy because the top ones have n square degree, while the bottom ones have something like n plus 1. However, what's happened if I'm asking how many vertices do we need to delete? Again, you need some time to think, to realize that if I'm deleting the top vertex, where the problem was appearing, then I am introducing several extra problems, n square of them. So this is a bad option. However, if I'm deleting all those vertices, then I have deleted only n. Well, now I have a solution of s squared plus 1, sorry. So, however, if I'm deleting from one gadget all of those vertices, then I have a solution with n plus 1, and you can try to see that this is also optimal. So why those two examples? Obviously, I wanted to demonstrate that the two problems may have completely different behaviors. And that's why it's interesting to study the second one. Okay, so let me start with vertex irregularity. And again, The problem is to delete the minimum number of vertices such that the graph is locally regular. But in particular, we're going to talk about vertex-irregulator. The set we are deleting, it's called vertex-irregulator if give us the remaining graph to be locally regular. And so the question can be rephrased into finding a minimum locally regulator. So, what are some existing results from a previous work? First of all, the problem is NP-hard, even in subcubic planar bipartite graphs. It's NP-hard to approximate with any normal factor. And it's W2 hard parameterized by the size of the solution, and W1 hard parameterized by the treedepth and the feedback vertex set of the graph. What are the positive known results is that there exists a FPT algorithm parameterized by maximum degree plus the size of the solution. And there is another FPT algorithm parameterized by the maximum degree plus the tree width. So what our goal while we start this work was try to figure out what exactly happens with other parameters. And we would like to find some parameters that settle the problem in FPT without the maximum degree. Okay, so what we managed to do, to have some FPT results that you can compute a minimum vertex regulator parameterized by neighborhood diversity, vertex integrity, and cluster deletion number. So let me start with the FPT algorithm about vertex integrity. And the definition for vertex integrity for some of those that are not familiar with, the idea is that you have a small set of vertices that you can delete from your graph, and then all the connected components also have a really small number of vertices. Okay, formally it's there. So, but that's the big idea. You have a small number of vertices, delete them, and then all the components are small. So how we're going to try to utilize that? So in the first step, you can easily guess the intersection of your vertex regulator with the set that you need to delete in order to have the small components. Then you try to compute the number of vertices that need to be in each component. And to do that, you're going to try some integer linear programming, where you can group some components between them and try to say that they're going to have the similar behaviors. So let's see what I mean group components between them. The idea is if two components with respect to the deletion set, they are isomorphic, then they're going to be in the same group. So for example here, the two first are isomorphic with respect to the deletion set. So this set in the top is the S. Okay, so those two are isomorphic with respect to S, but the third one is not. So those two are in the same group. Now, we want to define some behavior of the components of the same type. So how we can do that? So looking again in this specific kind of component, and the behaviors that we have are four. Is I'm not deleting any vertex of the component. I'm deleting just the top vertex of the component. I'm deleting just the bottom vertex of the component, or I'm deleting both of them. Someone can also see that every component needs to have some kind of behavior. So the sum of the different components needs to be the number of graphs we have of that specific component. And that's how we're going to use integer linear programming to compute everything. So, okay. Finally, we just need to create some constraints to guarantee that they are locally regular. For example, here, Here I don't have any problem, unfortunately. But for example, let's say this second behavior, if this is exactly the final instance, then I see that there exists a vertex in this component which has exactly the same degree as the vertex on the set, and we don't want that to happen. So that's that kind of constraints we are introducing, and it's not hard to deal with it if we know the number of components that have each behavior. Okay, so then let me, well, we're using some integer linear programming. It's FPT by the number of types, and the types are FPT by the size of vertex integrity. So then we decide to see what happens with the distance to cluster, cluster deletion number. Here you have a small number of vertices, you delete them, and then you have a cluster. So all the connected components are cliques. Now we're going to use the previous algorithm basically. And the key observation here is that if you have two twins inside the clique, then you're always going to delete one of them, regardless of what happens to the rest of the graph. So after you're doing that, then you're realizing that inside of each clique, you don't have more than 2 to the distance to clique vertices, because the only change is the neighborhood in the deletion set. Perfect. So now we have a graph with vertex integrity, deletion, the deletion number plus the 2 to the deletion number, and running the previous algorithm. Okay, so let me move forward and go to distance to edge, local edge distance to local irregularity. So similarly to the previous problem, we're defining an edge regulator, where is a number of edges that you are deleting them and you have a locally irregular graph, and we want to find a minimum size edge regulator. And this is the problem that we introduce here. So all of the results that I'm going to present now are ours in this paper. And the first result is the problem is extremely hard, is hard in planar bipartite graphs of maximum degree 4. And is W1 parameterized by the size of the solution. Okay, and I have them in reverse. So by the feedback vertex set number, by the tree depth, and by the size of the solution. What positive results we have? Unfortunately, only one, which is it's FPT parameterized by vertex integrity. And someone can realize that the vertex integrity algorithm is almost the same as the previous one, but instead of counting deletion of vertices, we're counting deletion of edges. So instead of presenting the positive result, I'm going to present one reduction. Phoebus is happy. So I'm going to present you the hardness parameterized by tree depth or feedback vertex set. And this reduction is based on a problem called general factors. So let me spend some time to give you the definition for general factors. The general factors is a problem, even in bipartite graphs, you have for each vertex a list of degrees, and your goal is to delete some edges. So in the final graph, each vertex has degree inside in their list. And this is also known to be W1 hard parameterized by one of the two bipartitions, the smallest. So what is the idea here? We are starting from an instance of general factors, and then we're going to try to add some gadgets to each vertex that are related to the degrees that we are not allowed to have. So basically, if in some vertex you have saying that you cannot have degree 1, then you need to add a gadget that will forbid this vertex to be degree 1. That's the idea behind it. So we're adding several of those gadgets in order to force all the restrictions, and then we're going to try to prove the equivalence of the solution. So let me spend some time to give you the gadget. So now I have fixed a degree that I don't want to use, and UI is the original vertex of my graph, and AJ there is the degree that I don't want to have in the final graph. Now, we are adding several trees, so basically you're forcing the two vertices to have the same degree. You also need to add some leaves there. And then why this gadget is like this is because I want to force the deletions to be from my original graph. So here, if I'm not deleting edges from my original graph and I'm deleting from the gadget, what it happens is forces this vertex here, if you delete one edge that is incident to that, it's forced to have the same degree with some vertex in the first set. So I have n square such stars, therefore I need to delete at least n square vertices. If you have two n square edges, if I have two deletions from here, I will have problem there, etc. So this forces us to have either a small number of deletions less than n square or something bigger than n square. And that's the key thing in order to have the reduction. So yeah, I'm saying that I'm adding several of those gadgets. Then the edge regulator either has size at most n square or it has more than that. And then those gadgets are forbid us to use those edges. And then we need to show that, okay, if I have an edge regulator, I can compute a solution for general factors and vice versa. What happens here is the deletions are all from the original graph, and we have forced to not have a degree that is not in the list. So it should be a solution for general factors. And the solution from general factors give us a specific degree that appears in its list, so it's not in the bad degrees that we have forced to exclude. So we should have a solution for edge-irregulator. Okay, so why this graph has bounded feedback vertex set and bounded tree depth? If I'm returning here, you can see that I have had only trees. If you add trees, you are not increasing the feedback vertex set, and the original parameter was one of the bipartitions. So you are deleting that and you are in a forest. Perfect. And also, the depth of those graphs are small. So when you consider tree depth, again, imagine that I'm deleting one of the two bipartitions and I'm ending up with a forest of small depth. So the tree depth, it should also be bounded by the parameter. Now, let me try to finish with this thing and explain what this says. So basically, this is the image we have for the problem. So the red line, which is not really red there, this is the red line which says for which problems we know that the problems, both of them are W1 hard, which parameters, and this goes up in contrast with what Dusan would like.
No, I think
the vertex cover is, you light it that way?
yes, this is the correct.
Okay.
So on the right
I prefer it the other way. So the problems is hard for those instances. Then we have this blue line that indicates that the vertex-irregulator is FPT for those parameters, and the olive line that indicates that those parameters here are setting the edge-irregulators to FPT. Now, in my opinion, the most interesting thing is that we cannot do the same as in edge we cannot do the same in edge regulators as in vertex regulators and generalize the vertex integrity algorithm for cluster deletion, because suddenly it's much more complicated to deal with clicks, especially if you change the small degrees here and there. We have no idea how to deal with big clicks in the edge version. Also, it would be interesting to see about modular width, because someone can imagine that, okay, in modular width, we have those sets of vertices incident to other sets of vertices. Each of those sets should be irregular. So maybe there exists some kind of idea to say that prove some properties for each bug and try to deal with the outside later. But not sure how and what we can do. Thank you so much.
Just to ask about, so it's easy for vertex cover, but hard for feedback vertex sets. So there is a plenty of things in between.
Yes.
Like B-part vertex cover is my favorite, but maybe any like modulator to linear forest or something like that.
Yeah, we haven't really tried to do that. Also, maybe it has some sense because for paths, the problem should be easy. For vertex regulators, we had some results in the past about paths.
Not
So
completely characterized paths.
yes, but after you add something, I'm not sure if it's become extremely harder or not. But yeah, that could be an interesting. Also, I was thinking at some point maybe to try to see if there is a polynomial kernel for vertex cover, but I don't see it at all.
Maybe I missed it, but what is this omega in the spin cover?
Okay, this is the usual notion in order to say that you also have a bounded size of click. So the biggest click in your graph has size omega.
Yeah.
And if you include it in the parameter, suddenly it's zero.
So without bounded click size,
It's across the
It's
line.
it's the gray area that we don't know.
Okay.
So we know for vertex regulator, because if you, like I was saying, if you have twins, you can delete them and suddenly the click size becomes small, because the only difference is some specific set. But for edges, no idea what's happening.
Let's send the speaker here.